Welcome to the boring cosmos, where the wonders of the universe are told slowly, in detail, until sleep comes and the stars keep watch. Tonight, we imagine a journey few could ever take, a journey into the most mysterious objects in the universe. This is what would happen if you fell into a black hole. Black holes are places where gravity has grown so strong, so absolute, that not even light can escape. They are not holes in the usual sense, but regions of space where the rules we know collapse under their own weight. To understand what it would be like to fall in, we must first get close. The black hole we will visit for this thought experiment is a stellar mass black hole, the kind formed from the collapse of a massive star. It's about 10 times the mass of our sun, but packed into a sphere only about 30 kilometers wide. Imagine all that mass, all that gravity, in something small enough to drive around in an afternoon. But the gravity here is not gentle. Long before you reach the black hole itself, its influence begins to dominate. At first, it's not dramatic. Spacecraft instruments pick up small increases in speed, small shifts in direction as the invisible pull grows stronger. The stars behind you seem the same. The silence of space is unchanged. But if you look carefully, you'll notice the light from stars ahead appears slightly bluer, their wavelengths compressed by your motion toward them. Behind you, light stretches and reddens, the colors fading as if your journey is pulling the warmth out of them. This is the Doppler effect on a cosmic scale. As you drift closer, your velocity increases without engines or effort. Gravity is doing the work. There's a sense of falling, though there is no air to rush past you, no wind in your face. The black hole remains invisible for now. You're still too far to see its shadow. All you notice is a region ahead where the stars seem fewer, a patch of space darker than the rest. As you close the gap, the change becomes clear. The patch is not empty. It is filled with light twisted into strange arcs. The black hole's gravity bends the paths of photons from background stars, warping them into rings and halos. This is gravitational lensing, one of the first hints that you are nearing an event horizon. The light looks wrong. No human eye has seen such distortions up close. It's mesmerizing and unsettling. Around now, your onboard clocks and signals back to Earth begin to disagree. To you, time feels the same. Seconds tick as they always have. But to an observer far away, your signals stretch out. Each moment you live takes slightly longer from their perspective. This is time dilation, a consequence of the black hole's immense gravity warping space-time itself. The closer you get, the more pronounced it becomes. Still, from inside your own journey, nothing feels different. Yet, the black hole is now a looming presence, not visible as a sphere, but as a perfectly black disk surrounded by a bright, warped halo of light from the rest of the universe. This is the photon sphere, where light orbits the black hole before escaping. It is not the event horizon yet, but already the view is alien. The stars seem to whirl and smear in impossible ways. If you look behind you, the universe is still there, but distorted. Ahead, the black hole swallows your gaze. At this distance, your ship's instruments scream warnings about tidal forces, the difference in gravity between your head and your feet. Here, they are still small enough to ignore, but with every kilometer forward, those forces grow. If the black hole were much smaller, spaghettification, the stretching of your body into a thin line, would already have begun. For now, you are still whole, still moving in one piece. You are past the point where escape would be practical. Even if your engines fired at full power, the fuel would burn for nothing. You are committed to the fall. The event horizon, the point of no return, is still ahead. There is no sign marking it, no line painted in space. From your perspective, it will feel like passing through any other point in the void. But the physics tells another story. Just beyond that invisible boundary, escape velocity exceeds the speed of light. No signal, no matter, no thought can ever return. As the pull strengthens, the warped light around the black hole becomes a ring, the accretion disk, if matter is falling in. In our journey, we'll imagine the disk is thin and faint, glowing with the energy of particles whipped to near light speeds. Its light is not constant. Patches flare as matter collides and spirals inward. The glow is harsh, but the black hole itself remains perfectly dark. Space and time, as you know them, are bending toward it. You are now minutes away from the horizon. The stars are gone from your forward view. All that remains is the black disk, the last light clinging to its edge. The sensation is not of moving faster, though you are, but of the rest of the universe slipping away. Every heartbeat carries you deeper into a gravity well from which there is no escape. Soon you will touch the horizon, and beyond it, the rules change. The black hole's event horizon stands before you, though you cannot see it as anything physical. In every direction, space is curved inward toward this invisible boundary. From far away, an outside observer watching your fall will never see you. Your image will slow, fade, and eventually freeze in place just outside the horizon, bathed in an ever-deepening red light as photons from your body are stretched into invisibility. To them, you become a ghost lingering at the edge of eternity. But from your perspective, the crossing is instantaneous. One moment, you are approaching a dark sphere framed by the distorted universe. The next, you are inside. And nothing in the laws of your personal experience tells you this has happened. There is no jolt, no shift in brightness, no sound to mark the transition. The reason is simple. The horizon is not a physical surface. It is a mathematical boundary in space-time. You pass it as easily as you cross an imaginary line in open space. And yet, the consequences are absolute. Once inside, every possible path forward in time also leads deeper into the black hole. The geometry of space-time here is so twisted that forward is no longer a direction you can choose. You cannot hover, cannot turn back. You are now part of the black hole's future in the most literal sense. Outside, the universe continues. Stars burn, planets spin, light travels endlessly. But none of it can ever reach you now. Your world has narrowed to a journey inward. The black hole's mass, compressed into a point called a singularity, pulls at you with unrelenting force. And yet, you do not feel this as a violent tug. Not yet. The scale of the black hole matters. In our case, this is a stellar mass black hole, only about 30 kilometers across. The tidal forces, the difference in gravitational pull between your head and feet, are already significant. If you were falling feet first, your legs are being pulled harder than your chest, and your chest more than your head. At first, it is a sensation, a stretch like the faintest pressure in a deep dive, but with every second, the gradient grows sharper. If this were a supermassive black hole, millions of times the sun's mass, you could cross the horizon without feeling any noticeable strain for hours. In such giants, the immense size spreads the tidal forces thin at the horizon, giving you a calm descent for much longer. But here in a stellar black hole, the compression and stretching intensify quickly. Your ship's hull groans under stresses no engineer ever intended it to bear. The light from the outside universe, visible if you look back, is now warped into a narrow, bright ring. It wraps around the horizon in strange arcs, smeared by gravitational lensing. Forward, there is only darkness. Not an empty darkness, but one so complete it feels like a physical thing pressing into your eyes. Time continues for you, but the outside universe will now play your story differently. Billions of years could pass out there before you touch the singularity, while you experience only moments. This is one of the strangest truths of relativity. Time itself is relative to where you are and how gravity acts upon you. Every second you move deeper into the black hole, the rest of the cosmos ages beyond imagining. Civilizations will rise and fall while you drift toward the center. Stars will burn out. Galaxies will If there were a way to send your gaze outward, which there isn't, you would see the universe's history accelerate. A fast forward of cosmic events until all that remained was darkness. But here, in your local frame, your fall feels steady, almost peaceful in its inevitability. The event horizon recedes behind you, but you can no longer think of it as behind. Space itself is flowing inward, like a river whose current carries everything toward the singularity. You are no longer moving through space. Space is moving you, and the river has no branches, no alternate paths. Deeper in, the gravitational gradient becomes unbearable. Your body begins to feel the slow, inexorable pull into a shape nature never intended. Spaghettification is not sudden, it is gradual. First, a slight pressure in your joints, then a stretch you can't resist. Your sense of your own body becomes strange. The difference between your head and feet feels larger than it should. This is not imagined. The tidal forces are literally elongating you, atom by atom, molecule by molecule. Inside the ship, the walls bow and stretch in the same way. No material resists, no technology exists to halt this process. All matter, living or not, obeys gravity's command. And then there's the light. Even within the horizon, photons can still travel short distances before being dragged inward. But the paths they take curve in strange ways. You might catch glimmers from your own ship's lights, bent back toward you from unexpected angles. Shadows twist unnaturally, forming patterns no human mind evolved to understand. The deeper you go, the more meaningless up and down become. All directions now lead inward. There is no reference frame that makes sense. Here, even the word falling is inadequate. You are simply existing in a space where the end is the same no matter what you do. Ahead lies the singularity, the point where density becomes infinite, where space-time's fabric tears in ways physics cannot yet explain. No signal has ever emerged from there. It is the edge not only of space, but of knowledge itself, and you are being carried to it second by second by the most powerful force in the universe. Inside the event horizon of a stellar mass black hole, the tidal forces are no longer something you can ignore. The difference in gravitational pull between your head and your feet grows at an exponential rate. Every moment brings a greater imbalance, stretching you along your vertical axis while squeezing you inward from the sides. This is not just uncomfortable, it is a fundamental reshaping of your body at the atomic level. The term scientists use, spaghettification, may sound almost humorous, but in reality it is one of the most extreme processes in the universe. Imagine a steel rod being pulled from both ends until it thins into a wire. Now imagine that the rod is made of living cells and that the stretching happens not in a factory, but in the silent void of space, where no material can resist gravity's demand. Your ship stretches too. Bulkheads that once stood rigid begin to lengthen. The instruments warp slightly. Even light behaves differently here. If you shine a beam forward, it curves toward the singularity before it has traveled more than a few meters. The path of every photon is bent inward, unable to resist the gradient of space. Even if you were to shine light backward toward where the horizon used to be, it would arc and eventually spiral down into the same destiny as you. The interior of your ship is becoming an alien environment. The air seems thicker, not because of any change in its composition, but because your perception is warped by the strange geometry you now inhabit. Every step forward feels as though you are walking uphill, though there is no ground here, only the invisible pull of space-time itself. Time for you moves at its normal pace, but the outside universe is rushing far ahead. If you could somehow look back past the horizon, which you cannot because the geometry has sealed it away, you would see a version of the cosmos billions of years older than the one you left. Stars would flare and fade in instants. Entire galaxies would shift position in seconds. The great slow dance of the universe would play out as a frantic blow. And yet here, inside the black hole, you are trapped in a singular path toward the center, each meter bringing you closer to a place physics does not yet fully understand. As you fall deeper, the concept of downed becomes meaningless. There is no central floor, no fixed point you can orient toward. Instead, all geodesics, the natural paths through space-time, converge inward, not toward a location in three-dimensional space, but toward a moment in time that is unavoidable. In this sense, you are not falling into a place, you are falling into the future. Your instruments, still struggling to measure anything meaningful, detect a rise in gravitational curvature so steep it defies comprehension. The numbers climb into infinities your onboard computer cannot display without errors. The black hole is not just a point of intense gravity. It is a region where the very coordinates of space and time collapse into a singular destiny. If you were outside watching someone else fall in, you'd see them freeze at the horizon, their image dimming as the wavelengths of their light stretched into oblivion. But inside, from your point of view, your fall accelerates. You cannot hover or change speed. You have no control now. Gravity owns you completely. Every second is now a battle between the structure of your body and the differential pull of the singularity. The atoms in your feet are being tugged with more force than those in your head, and the stress rises beyond what chemistry or biology can sustain. Soon, your nervous system would fail. Consciousness might flicker as the signals between your brain and body distort under the strain. But let's imagine, for the sake of our thought experiment, that somehow you remain aware, that your mind remains intact enough to observe the journey. The world around you is a swirl of warped space. Shapes lose their meaning. You might see distorted echoes of your own image, bent back toward you in fragments by the warped geometry. Behind you, if behind has any meaning here, the light from the accretion disk outside the horizon still filters faintly inward, scattered and weak, but it no longer forms a coherent picture of the outside universe. It is more like a fading memory than a view. Deeper still, the tidal forces grow so immense that even the smallest components of matter are affected. Quarks, the fundamental building blocks of protons and neutrons, would experience forces pulling them apart, something not seen anywhere else in the universe, except perhaps in the first moments after the Big Bang. No other environment pushes matter to such extremes. There is no pause button, no way to slow what is happening. In a stellar black hole, the fall from the horizon to the singularity is swift. For you, It might take only seconds before the full force of spaghettification tears molecules apart. Your body becomes a thin, elongated stream of particles, stretched across kilometers in an instant. But in our imagined journey, we will slow the clock, allowing your awareness to continue so we can describe the final approach. As you fall, the singularity grows closer, not as an object you can see, but as an unavoidable destination. Space is no longer something you move through, it is something collapsing around you. The singularity is not ahead of you like a mountain peak, it is in your future, the same way next Tuesday is in your future. You cannot choose to avoid it any more than you can choose to avoid the next moment of time. The temperature rises in strange ways here, not because of heat in the usual sense, but because particles falling with you are being accelerated and compressed, colliding and releasing energy. Radiation fills the space around you, though you can't measure it in ordinary terms. Your instruments detect particles moving at near light speeds, their trajectories curling in impossible arcs. The final stages are close now. Every trace of the universe outside is gone. Only the interior geometry remains, a funnel of inevitability drawing you into the ultimate unknown. And in the silence of this descent, you realize you are about to encounter something no one has ever returned to describe. The singularity lies ahead, though ahead no longer means what it once did. Inside the event horizon of a stellar mass black hole, space and time have traded roles. What you once thought of as forward is now inevitable, not because you are moving toward it, but because space-time itself is flowing that way. Every second of your existence is now a step deeper into the future of the black hole. There is no staying still here. Imagine a conveyor belt with no edges, moving at the speed of light toward a single destination. You are not walking along it. You are part of it. There is no choice, no maneuver, no possibility of escape. The singularity is not a physical object you could touch or orbit around. It is a region where density becomes infinite, where all known laws of physics break down. It is a boundary not just in space, but in understanding. Our current models, the equations of general relativity, can describe your fall all the way to this point, but they cannot describe what happens inside it. At distances this small, quantum mechanics should also matter, and yet our theories fail to unite the two. This is why the singularity is called a place of infinite curvature, a term that means our mathematics has reached its limit. Your descent toward it is like heading into a region of a map where the paper simply ends. Up to now, the stretching forces have been tearing at you relentlessly. The differential gravity between your feet and head has been growing stronger with every moment. In a stellar mass black hole, this journey from horizon to singularity is measured in seconds. From your perspective, you might feel those seconds stretch into minutes, but not much more. And yet, even in this brief span, the changes are profound. Your body, your ship, and everything you carried are no longer solid objects. They are elongated streams of subatomic particles, each following its own trajectory inward, yet all converging on the same fate. The concept of you as a coherent form has already ended, and still, in our thought experiment, we allow your consciousness to persist, not because it could in reality, but because the story of what happens here demands a wit. There is no light here, except a faint radiation from particles falling with you. That light is quickly redshifted into invisibility. In practical terms, you are falling into darkness so complete that even the idea of seeing becomes meaningless. Your other senses are equally useless. There is no sound, sound care a medium, and space offers none. There is no smell, no taste, no texture. The only reality here is geometry, space-time collapsing inward toward an infinitely small point. Outside, the universe has already aged into epochs you could not have imagined when you began your journey. Stars like our sun have burned out. The Milky Way may have merged with other galaxies, becoming part of a vast elliptical swarm of stars. Entire civilizations could have risen and vanished without you ever knowing. You are now in a place disconnected from that flow, moving toward a destiny that no external event can change. As the singularity approaches, distances lose meaning. The gravitational curvature is so extreme that the very idea of meters or seconds becomes slippery. The mathematics says you will reach the singularity in a finite amount of your own proper time, and when you do, you will cease to exist in any meaningful form. Matter itself will be crushed to infinite density if our current models are correct. In the last fractions of a moment before that, tidal forces become absolute. Every dimension of your being is stretched and compressed beyond any physical analogy. The stream of particles that was once your body narrows into a filament of unimaginable thinness. Yet still in our slowed thought experiment, we allow some fragment of awareness to linger. If you could somehow send a signal outward now, it would never escape. The horizon behind you has sealed you incompletely. Not even hypothetical faster than light signals could bridge the gulf. You are causally disconnected from everything that is not falling alongside you. In a strange way, you are now part of the black hole's mass. Your energy, your particles, your very existence are contributing to the gravity that pulled you here. From the outside, nothing has changed. An observer far away would say the black hole's mass had increased by an amount equal to yours, but they would never see you arrive. They would see only the fading ghost of your approach, frozen forever at the horizon. Inside, you move inexorably toward the singularity. Some theories suggest that the singularity might not be the end. Quantum gravity, a theory we do not yet possess, could reveal a different outcome. Perhaps the singularity is not a point, but a passage leading to another region of space-time, another universe entirely. Perhaps the information that made you is not destroyed but transformed, encoded in ways we cannot yet detect. These are speculations, and they remain unproven, but they offer a small spark of curiosity in an otherwise final story. The reality, as far as we know, is that you will reach the singularity, and in that instant, all structure, all identity, all meaning will be erased, and with you every detail of your journey will vanish from the universe's record, except for the faintest whisper in the black hole's mass and spin, a trace no one will ever read. You are seconds away now. Those seconds are barely real here. The singularity is not a place you can see ahead of you. It is the inevitable conclusion of the path you are on. And as you approach, you realize that this is not just the end of your fall, it is the end of everything you have ever been. As the singularity draws near, reality itself begins to feel like a fragile illusion. You have been falling for what seems like mere minutes, but your path has already taken you further from the rest of the universe than any traveler could ever hope to return. For all practical purposes, you are lost to history. The question now is not whether you will reach the singularity, that is inevitable, but what will happen when you do. In classical general relativity, the answer is simple and merciless. You are crushed into a point of infinite density. Space and time themselves terminate at this point, meaning there is no after to consider. Your atoms, your subatomic particles, even the space-time fabric they occupy, collapse into a state where the laws of physics, as we know them, no longer apply. This is the cold mathematical truth Einstein's equations give us. But human curiosity has never been satisfied with a simple end. Physicists have spent decades imagining other possibilities, because infinity, in science, is a sign that our understanding has reached its limits. One idea is that the singularity could be avoided entirely by quantum effects. According to some versions of quantum gravity, the collapse might stop at an extremely small but finite size, creating an object called a Planck star. Such a star would be unimaginably dense, far denser than a neutron star, but not infinitely so. If true, this would mean the inside of a black hole has structure, and the singularity is just a mathematical artifact of incomplete theory. Another theory suggests that a singularity could serve as a bridge, a tunnel through space-time leading to another region of the universe, or perhaps another universe altogether. This is the idea behind a wormhole. If the geometry of space-time permits it, you could pass through the black hole's interior and emerge elsewhere. The trouble is, such wormholes may be unstable, collapsing before anything could pass through. Without exotic forms of matter to hold them open, matter with negative energy density, they would pinch shut too quickly for you to survive the trip. Then there is the idea that black holes might encode all the information about what falls into them on their event horizon. This is the holographic principle, inspired by the work of physicist Gerard Hooft and later expanded by Leonard Susskind. According to this, you and every detail about you might still exist in some form, smeared across the horizon as quantum bit. You would not be alive in any conventional sense, but the information that once described you would not be lost. It would be preserved, though inaccessible, until the black hole itself eventually evaporates through Hawking radiation over trillions upon trillions of years. From this perspective, your end is less an erasure than a transformation into a different kind of existence, one bound to the surface of a sphere that can never release you until the cosmos itself has grown cold. And then there are more speculative ideas, ones that tread into the territory of science fiction but remain grounded in mathematical possibility. Some researchers have proposed that the core of a black hole could bounce, creating a white hole, the time reverse of a black hole, which expels matter and energy rather than pulling it in. If this is the case, you might someday be ejected into a completely different era of the universe, perhaps even into its far future, when stars are gone and galaxies have faded into the cosmic night. In such a vision, your fall into the black hole would not be a one-way trip to oblivion, but a passage through the deepest tunnel in space-time, spitting you out in an alien epoch where nothing familiar remains. Of course, all of this is speculation. None of these scenarios has been proven, and without direct observation, they may remain forever beyond our reach. From your perspective inside the black hole, these possibilities are no comfort. You are not drifting toward a new dawn. You are hurtling toward a final moment where space collapses entirely. Even if a wormhole or white hole existed ahead, you could not steer toward it. You are being carried by the geometry itself, with no agency left. The closer you get, the stranger time becomes. It does not pass in the same rhythm. The final milliseconds before reaching the singularity may feel stretched, elongated, as though your mind is trying to cling to each moment. Or perhaps they flash by instantly, your awareness snuffed out before you can register the change. In these last instants, you might wonder if reality outside the black hole even continues. For all you know, the outside universe could already have met its own end. You have been cut off for so long, in terms of causality, an eternity has passed. Your reality is now bounded entirely by this descent. The singularity is no longer something ahead of you, it is the final frame of your existence, and you are already inside its gravitational script. And then there is the moment when no theory can speak for you. Whether it is the infinite compression of general relativity, the rebirth into another universe, the slow storage of your information on a cosmic hologram, or the violent expulsion into a white hole, that moment is yours alone. No light will carry the news of it. No observer will ever know the details. You will cross into a place where the language of physics fails, and in that instant, every question about your fate will be answered, but only for you, and only for the briefest flicker of what can be called time. From your perspective inside the black hole, the journey to the singularity is short and absolute. But to someone watching from a safe distance, the story looks very different, almost hauntingly so. Imagine a spacecraft hovering far from the event horizon, its instruments trained on you as you fell toward the black hole. At first, they would see you moving normally, accelerating as the pull of gravity grew stronger. Your ship might flash faint signals back to them, pulses of light carrying data about your descent. But as you neared the event horizon, something strange would happen. Your motion would seem to slow. The further you came to that invisible boundary, the longer it would take for each new signal to reach the observers. From their point of view, you would never actually cross the horizon. Instead, you would appear to freeze just outside it, hanging there in space, suspended in an eternal fall. This is not because you stop, but because time itself behaves differently near such extreme gravity. The light carrying the image of you is stretched into longer and longer wavelengths, a process called gravitational redshift. At first, your ship's image would take on a faint, reddish tint. Then it would deepen, fading into black as the wavelengths became too long for human eyes to see. Eventually, no visible trace of you would remain. Even sensitive instruments would struggle to detect your presence as your photons stretched into radio waves and beyond. In a sense, you become a ghost, still there, still falling, but unreachable in both space and time. The most eerie part is that from the outside, your fall takes forever. Observers could watch for 1,000 years and you would still seem to linger just at the edge. In their view, you are trapped on the surface of the event horizon, never completing your journey, never quite disappearing. This strange effect is a direct result of Einstein's general relativity. Time near a massive object runs more slowly than time far away. The stronger the gravity, the greater the difference. Near a black hole, the difference is infinite. Inside your ship, you might experience only seconds between crossing the horizon and reaching the singularity. But to the rest of the universe, that last instant is drawn out into eternity. Even your last words, if you tried to send them, would arrive increasingly delayed, stretched apart, until the pauses between them became longer than the age of the universe itself. From the observer's perspective, the black hole itself changes as you fall. Its mass increases by the exact amount of your ship and your body combined. But the way this increase happens is subtle. They never see you vanish into the hole. Instead, the horizon seems to expand, enveloping your frozen image. Your ship's energy, momentum, and information are absorbed into the black hole's surface in a way consistent with the holographic principle. To them, you have not fallen into the center, but become part of the horizon itself, an imperceptibly thin layer encoding everything you once were. This view raises a profound question. If nothing can be seen crossing the event horizon from the outside, does the interior of the black hole even exist in the same sense we think it does. Some physicists argue that the interior is just a mathematical convenience, that all the physical reality of a black hole exists on its surface. Others hold firmly that the interior is as real as anything else in space-time, but sealed off forever from the rest of the universe. The outside observer would never know which is correct. Their instruments could only measure the black hole's external properties, mass, electric charge, and this is the essence of the no-hair theorem. All the rich details of what fell in are hidden forever, leaving behind only a few numbers. If they looked long enough, they might detect tiny fluctuations in the black hole's surface, ripples of space-time created when your mass merged with it. These ripples, known as gravitational waves, would radiate outward at the speed of light, carrying the news of your fall across the cosmos. But they would carry no image, no voice, no memory of who you were. Only a faint pattern in the curvature of space would remain, fading into the background of cosmic noise. From their perspective, you are gone without ever leaving, present without being reachable. And here is the strangest truth. Both views, yours inside the black hole and theirs outside, are equally real, even though they cannot be reconciled. In your frame, you crossed the horizon long ago and are now seconds from the singularity. In theirs, you are forever on the brink, never crossing at all. General relativity allows both realities to coexist because time and space are not absolute. They depend on the observer's position and motion. This means that in some deep sense you are still there at the edge, falling forever, and also already gone, swallowed by the singularity. This duality is not something we see in everyday life. It exists only in the most extreme environments, and black holes are the ultimate stage for it. From the outside, your story is an eternal approach, with no conclusion. From the inside, it is a brief and final plunge. Both are true, but neither can be told in full to the other. And so, as your image fades completely from their instruments, the observers are left with only the black hole itself, a little more massive, a little larger, and just as silent as before. Whatever happened to you beyond the horizon will remain a mystery to them forever. From the outside, a black hole looks eternal. It swallows matter and light without effort, growing more massive over time. To the casual observer, it seems like nothing could ever destroy it. But Stephen Hawking changed that view forever in 1974, when he showed that black holes are not completely black. Through a strange quantum effect near the event horizon, they emit tiny amounts of radiation, now known as Hawking radiation. This process is unimaginably slow for large black holes. A stellar mass black hole, one few times the mass of our Sun, would take far longer than the current age of the universe to evaporate. But in principle, it means that no black hole lasts forever. To understand this, imagine empty space near the event horizon. According to quantum mechanics, empty space is never truly empty. It constantly produces pairs of virtual particles, one matter particle and one antiparticle. Normally, these pairs annihilate almost instantly, disappearing back into the vacuum. But near a black hole's event horizon, something unusual can happen. If a particle pair forms right at the horizon, gravity can pull one into the black hole, while the other escapes into space. The escaping particle becomes real, carrying energy away. To conserve energy, the black hole loses an equivalent amount of mass. Over time, this slow leak of energy causes the black hole to shrink. For an observer outside, the process is invisible at first. The black hole's immense size means that the loss is negligible. For millions, billions, even trillions of years. It continues to dominate its surroundings, swallowing gas, dust, and stray stars, easily replacing any mass it loses through radiation. But imagine a future where the universe has aged beyond recognition. Stars have burned out, galaxies have gone dark. The cosmic microwave background, the afterglow of the Big Bang, has cooled to near absolute zero. Only black holes remain as the last major structures in the cosmos. In this far, far future, Hawking radiation becomes the dominant force, shaping their fate. Slowly, they begin to shrink. For a supermassive black hole, the kind that sits at the center of galaxies, this process could take 10 next years or more, a number so large it defies intuition. But eventually, the mass will fall low enough that the black hole's temperature, which is normally near absolute zero, begins to rise. Unlike normal stars, which cool as they lose energy, a black hole gets hotter as it gets smaller. This sets up a runaway effect. The hotter it gets, the more radiation it emits, and the faster it loses mass. By the final stages, what was once an object billions of times the mass of the sun could be no larger than a mountain. Its temperature would soar, releasing radiation at a furious rate. In its last moments, the black hole would emit an enormous burst of energy, the final evaporation of everything it ever contained. What would that mean for what fell inside? The laws of quantum mechanics tell us that information cannot be destroyed. This leads to one of the greatest puzzles in modern physics. If everything that falls into a black hole is eventually emitted as Hawking radiation, where is the information stored? Is it somehow imprinted on the radiation in a scrambled form, as some theories suggest, or is it lost forever, violating a fundamental principle of physics? This information paradox has sparked debates for decades. Some physicists believe the information is preserved on the event horizon itself in a kind of holographic form, slowly released with the radiation over time. Others suspect that our current understanding of space-time must be incomplete, and that a full theory of quantum gravity will reveal the answer. For you, the traveler who fell in long ago, this offers a strange kind of immortality. Even though your body, your ship, and every trace of your former self were destroyed at the singularity, the quantum information that once described you might still exist, scattered across the horizon and gradually radiated back into the universe over unimaginable spans of time. But what form would that take? Certainly not the reassembly of your mind or the revival of your journey, rather the release of your data into the vast cold nothingness of a dying cosmos. There would be no one left to see it, no civilization to detect the final flash of light from the black hole's death. The energy would ripple through an empty universe, fading into the background as the last structures dissolved into heat. The black hole's slow death marks the closing chapter, not just for itself, but for an era of the cosmos. After the last one evaporates, there will be no more gravity wells to trap light, no more massive objects to shape the fabric of space. Only particles and radiation will remain, drifting in an endless cold expansion. This is the ultimate fate of the universe in a scenario dominated by Hawking evaporation, a heat death where entropy reaches its maximum and no process can create structure again. For the black hole that claimed you, its end will come long after everything else has faded. The burst of energy it releases will be the last bright moment in a universe that once teemed with galaxies, stars, and light. And in that instant, the chapter on your fall will close, not with a scream or a cry for help, but with a silent conversion of matter into pure energy, dispersing into the infinite night. Until now, we've imagined your fall into a stellar mass black hole, an object just a few kilometers across, born from the collapse of a massive star. In such a black hole, the tidal forces near the event horizon are extreme, tearing you apart within seconds of crossing. But the universe also contains supermassive black holes, millions to billions of times the mass of our sun, sitting at the centers of galaxies. The one at the heart of the Milky Way, Sagittarius A, is over 4 million solar masses. Others, in distant galaxies, grow to tens of billions of solar masses. Falling into one of these giants is an entirely different experience. The first difference is scale. A stellar mass black hole might have an event horizon only tens of kilometers wide. A supermassive black hole's horizon can span millions of kilometers, large enough to engulf entire planetary systems. The immense size means the curvature of space-time at the horizon is much gentler. You could cross it without feeling any dramatic tidal stretching. No spaghettification, at least not yet. From your perspective, nothing special happens at the horizon itself. Your ship's instruments might detect the extreme warping of light, the gravitational lensing bending the view of the universe into a ring-like halo, but physically, you would feel almost weightless. The pull is still there, but it's spread over such a vast region that the difference between the gravity at your feet and at your head is imperceptible. This makes the experience deceptive. You might think you have time, perhaps hours, days, or more, to explore the region inside the horizon before reaching the singularity, and you would be right. In a supermassive black hole, the journey from the horizon to the center could take hours, or even longer in your own frame of reference. But it is still a one-way trip. The same inevitability rules here as in a smaller black hole. Once you cross the event horizon, you are trapped. No amount of acceleration, no rocket, no force in the universe can bring you back out. The path ahead is set. Inside, the view would be unlike anything else in the cosmos. Light from the universe outside would be compressed into a shrinking, distorted patch behind you. The rest of your view would be dominated by darkness. Not empty black, but a featureless void where space-time itself is flowing in. Around you might be other objects falling at the same time, gas clouds, dust, perhaps even whole stars captured by the black hole's pull. And falling matter in a supermassive black hole can form an accretion disk outside the horizon, heating to millions of degrees and blazing brighter than entire galaxies. But once inside the horizon, that brilliance vanishes. All light is inward bound now, unable to escape. The strange part is how peaceful it might feel at first. Without the intense stretching you would experience in a smaller black hole, you might be lulled into thinking there's still time to turn around. Your ship's navigation system might still show velocity and position, but the coordinates have lost their meaning. Space itself is curved so severely that forward and downward are now the same thing, and both point toward the singularity. As the minutes pass, the geometry changes. The tidal forces grow, slowly at first, then exponentially. Somewhere deep inside, perhaps thousands of kilometers past the horizon, you begin to feel the stretch. It's subtle, a faint pressure pulling along the axis toward the center. Then it grows stronger. Soon your body and your ship are being drawn into a narrow, elongated shape. Spaghettification begins in earnest, but here it takes much longer. You might have minutes, even hours to experience it before the final destruction. This drawn-out process makes the journey far more surreal. In a stellar black hole, death is instantaneous once you near the center. In a supermassive one, you have time to think, to observe, to wonder what the singularity will be like when you reach it. From the outside, the same rules apply as before. An observer will never see you cross the horizon. They will see you slow, fade, and vanish into the red-shifted shadow of the black hole. For them, you remain forever on the edge. For you, the descent continues without pause. If Sagittarius A were your destination, you could imagine this fall as a kind of silent, slow-motion dive into infinity. The singularity would still await you at the center, and when you finally reached it, the outcome would be no different than with its smaller cousins: the crushing density, the breakdown of known physics, the end of all structure. All of it is inevitable. The only difference is the grace with which it happens. Instead of a violent tearing within seconds, your destruction is a long, quiet unwinding. The larger the black hole, the gentler the entry, but the same finality. And here's an unsettling thought. Because supermassive black holes take so long to evaporate through Hawking radiation, any information you carry into one could be locked away for inconceivably longer than in a smaller hole. You could fall into one of these giants and be sealed away, encoded on its horizon until long after every star in the universe has died. In that sense, a supermassive black hole is less like a quick end and more like an eternal tomb, a perfect vault that will outlast almost everything else in the cosmos. Inside the black hole, there is no escape and no pause. Space itself is flowing toward the center, and you are carried along as if trapped in a cosmic waterfall. The singularity is not just a point in space, it is a moment in time, your final moment. In a normal environment, you can move in 3 dimensions, forward or backward, left or right, up or down. Inside the event horizon, one of those directions, the one leading toward the singularity, is no longer a place you can avoid. It is as inevitable as tomorrow. Even if you fired your engines at full power in the opposite direction, you would only reach the singularity slightly faster. In the early part of your descent, the singularity is still far away. You may be hundreds of thousands of kilometers from it in a supermassive black hole, or only a few kilometers in a stellar one. But distance here is misleading. The geometry of space-time is so warped that your path curves inward in ways your mind cannot picture. The clocks on your ship still run, but their meaning is warped too. Time is no longer an independent dimension you move through. It is bent and pulled toward the singularity, along with space. As you draw closer, the tidal forces become impossible to ignore. Even in a supermassive black hole, where the initial crossing was gentle, the gradient of gravity becomes steeper. The pull on your feet is now significantly stronger than on your head, and this difference grows rapidly. Your body begins to stretch, your structure elongating in the direction of the pull. If your ship is still intact, its frame groans under the strain. The walls bow slightly, invisible at first, but measurable. Your instruments might still function, but their readings grow meaningless. Directions lose their meaning. Every path leads inward. The closer you are, the more space collapses into that single future. Light from the singularity does not exist. It is not an object that shines. Instead, you see only darkness ahead, not like a shadow, but a void beyond perception. Behind you, the outside universe is compressed into a tiny, distorted patch of light, warped into strange arcs and streaks by gravitational lensing. Stars that once filled the sky are now crowded into a thin halo. You might see flashes, the last photons from distant supernovae or gamma-ray bursts, bent into your field of vision by the immense curvature of space-time. In these final moments, physics as we know it begins to fade. General relativity predicts that the singularity has infinite density, but infinities in science are often signs of an incomplete theory. Quantum mechanics, the theory of the very small, tells us that space-time should have a discrete, granular structure at incredibly tiny scale. The clash between these two theories means that what truly happens at the singularity is unknown. Some researchers suggest the singularity might be replaced by a finite, ultra-dense core, perhaps a Planck-scale structure where quantum gravity takes over. Others speculate that the collapse could lead to a bounce, creating a new region of space-time, maybe even a new universe. But from your perspective, these possibilities are meaningless. You are not a theoretical model. You are a traveler, and your trajectory ends here. The gravitational forces rise to overwhelming levels. Molecules are torn apart, atoms are stripped of their electrons, nuclei are crushed together into a soup of subatomic particles. Even these particles may not survive the journey intact. Quarks and gluons, the smallest building blocks we know, could be forced into states we cannot describe with current physics. Time dilation now reaches extremes beyond imagination. For you, the singularity is seconds away. For the outside universe, if any observer still exists, countless eons might pass in that span. You might wonder what has happened to the cosmos in that unimaginable interval. Have stars gone out? Have galaxies dissolved? Has the black hole itself aged toward its eventual evaporation? But you will never know. The singularity lies ahead like an unyielding wall in time, and you are moving toward it at the speed of inevitability. Then comes the final approach. The stretching force has surpassed any imaginable limit. Your body is no longer a body in any meaningful sense. It is a cascade of disassembled particles. The concept of you is reduced to a pattern of energy and quantum information, encoded in ways we cannot yet comprehend. At the very last instant, space-time curves so steeply that every direction becomes the same. There is no left, no right, no up, no down, only inward, only now and then. By the equations of general relativity, you reach the singularity. In the language of physics, this is where your world line, the record of your existence in space-time, comes to an end. Whether there is something beyond it is not for you to discover. You have crossed the final horizon, the one inside which not even the laws of the universe can guide you further. To an outside observer, you never reached this point. To you it was inevitable. And in that contrast lies the deepest mystery of all, the black hole's power to hold two contradictory truths forever apart. The singularity has claimed you. In the framework of general relativity, your journey has ended at a point of infinite density, where the curvature of space-time becomes absolute. There is no next moment, no forward path. If consciousness could somehow persist here, it would find no direction to move, no signal to follow, no sense of time passing. Yet for the rest of the universe, your story has never truly ended. You remain frozen in their sight, eternally falling, caught in the amber of warped space-time. If someone were watching from far away, perhaps a civilization orbiting a distant star, they would still see you suspended at the edge, even as their own world aged, their star dimmed, and their galaxy drifted into darkness. The light carrying your image would be stretched thinner and thinner until it blended with the faint hiss of the cosmic background, indistinguishable from the afterglow of the Big Bang. To them, you have become part of the black hole's skin, an encoded pattern within its surface, perhaps never to be read, perhaps to be slowly released across inconceivable ages as Hawking radiation. This dual existence, gone in your frame, eternal in theirs, is the strange gift and curse of a black hole. Your fall is both complete and forever in the far future, when the universe is quiet and cold, when galaxies have thinned to lonely collections of dying embers, the black hole that took you will remain an unlit monolith in an ocean of nothing. It will be silent, patient, and unchanging for eons beyond comprehension. Yet the laws of physics do not allow permanence. One by one, the black holes will evaporate, their horizons shrinking, their mass bleeding away as faint radiation. The process will be slow beyond measure, but it will not stop. The one that claimed you will grow hotter as it loses mass, emitting more energy in a final burst. When that moment comes, the very last echoes of your fall will scatter into the void, not as an image or a voice, but as photons and particles, random and unrecognizable, merging with the background radiation of a dead cosmos. And then, nothing, no trace of you, no trace of the black hole, no trace of the galaxy that once housed it. Only the endless expansion of space, cold and silent. It is tempting to call this an ending, but endings are a concept tied to time, and time itself loses meaning in this final state. The universe will not notice its own stillness. It will not remember, and yet your story remains worth telling, not because it has a triumphant conclusion, but because it reveals how strange and fragile existence can be when stretched against the infinite. Falling into a black hole is not just a plunge into darkness, it is an encounter with the limits of knowledge. It forces us to confront the edges of our understanding, where our greatest theories break and new ideas must take root. Perhaps somewhere in the framework of a theory we have yet to discover, the singularity is not the end. Perhaps it is a bridge, a transformation, a step into another realm of space-time, a realm we cannot yet imagine. If so, then the story of your fall is not over, merely paused in a chapter we cannot yet read. But here, within the bounds of what we know, your path has been written to its final line. You began among the stars, traveling through the ordinary fabric of the cosmos. You crossed into the event horizon, passed through a world where time and space bent into strange shapes, and approached the place where even those shapes dissolve. You have become part of the black hole's history, as it has become part of the universe, and in the fullness of time, both will fade into the same background, the quiet hum of eternity. As the last imagined words of the boring cosmos fade into silence, the black hole remains, steady and indifferent, a monument to the mysteries that still wait for us in the dark. And if sleep has taken you somewhere in this tale, you are now adrift in your own horizon, where the mind slowly sinks into its own quiet singularity. Out there, in the infinite night, the black hole waits, not as a predator, not as a trap, but simply as it is, the ultimate expression of gravity, the patient keeper of secrets, the silent witness to the long, slow passing of everything. The fall is over, the story is complete, and the universe goes on, stretching forever toward the unknown.